example of K-map, how to solve the sum of products with the help of the K-map. Now the case today we are going to discuss is when there are some don't care conditions and how to use these don't care conditions to solve the Boolean expression. Now let us first discuss what the don't care conditions are. Sometimes a situation arises in which some input variables are not allowed. As an example, when we consider the BCD numbers, and in BCD we have the BCD codes for 10 combinations from 0 to 9, that is for the decimal number. And as we are using 4 digits for the BCD number, that means we have total 16 combinations, out of which we are using only 10 combinations and the 6 combinations are remain unused. So these unused conditions or the unused states are known as don't care conditions. So there are 6 invalid combinations, 1 0 1 0 for 10, 11, 12, 13, 14 and 15, which is represented as 1 1 1 1, which are not used in the BCD. As we have done in the BCD addition, when there is a unused state, so what we do, we add +6 to the unused states and we get a valid BCD number. So when there is any unused state or denoted by either don't care or the cross, then it is known as don't care condition. Now we are going to discuss how we will handle it, how we will handle the don't care condition when we are using a K-map to solve the Boolean expressions. In such cases, since these unallowed states will never occur in an application involved in BCD code, therefore they can be treated as don't care terms with respect to their effect on the output. As we know, these conditions will never occur when we are representing a BCD number. That means we say that we don't care about these conditions and we have to proceed with our normal representation. The don't care terms can be used to advantage on the K-map, and let us see how it gives some advantage when we are solving K-map. Suppose this is a binary, a BCD input is a BCD number, and we have, according to the input, we have some outputs. So here these ones are the valid output, that is sum of product. Zeros are POS, product of sums, and beyond 9, that is from 10, 11, 12, 13 and 14, 15. These are known as the don't care condition. So in the truth table, what we have done, we have represented these don't care conditions with the help of cross. Many times in many author, you will find that in the books it is written as D, small d. So whichever is the representation, but in standard form, whenever there is a don't care condition, we'll represent it by a cross. So how to plot these conditions? We have plotted the ones, we have 3 ones, and one is for 0, 1, 1, 1. So here is 0, 1, 1, 1. This is your first one. Then we have one at 1, 0, 0, 0. So 1, 0, 0, 0. This is your first. So we have represented 1, 0, 0, 0. Then another one is at 1, 0, 0, 1. That is 9. So 1, 0, 0, 1. This is your 9. So we have 3 ones. And rest of the 6 combinations are don't care. So I have represented all remaining 6 combination according to their binary equivalent as a cross. So we have 2 options. If we are not considering the K-map, then if there is only ones, so one pair is this. So we can pair these 2 ones, and this one will appear a single. So when we are solving without the don't care condition, we'll get an expression like this. So without the don't care condition, this pair will result in here A and B across the pairing is constant, that is 1 0, and C is constant. When we are moving from this point to this point, then C is constant 0 and D is changing from 0 to 1. So we eliminate D and we are left with 1 0 0, and 1 0 0 is nothing but A, B bar, C bar. Now similarly for this, as this particular one is single, So we'll write its equivalent binary combination, and it is 0 1 1 1. That means it is A bar B C D. So this is how, when we solve without a don't care condition, the output will be solved output will be like A B bar C bar plus A bar B C D. Now to represent this particular combination, we need a AND gate with 3 input here. We need a AND gate with 4 input here, and we need a OR gate. So one 3 gate AND, one 4 input AND, and a OR gate. Now consider the case when we are using the don't care. When we are using don't care, then it will be octet. So we consider that these don't cares can be 1. So don't care means they can have a value 0 or they can have a value 1. So this is the condition how don't care is treated. So don't care is it may have a value 1, it may have a value of 0, but we don't care whatever is its effect on the output. So we consider that these don't cares are 1. So I have made an octet and I have made a pair for this one. So for this octet, we can see that A is constant when I'm moving from this position to this position. When row are changed, A is constant, and C, D are continuously varying throughout this pairing. So we get the first term, that is A, which is equals to 1, that is A. Now for this condition, for this pair, we have for this pair, A is changing from 0 to 1 when I move from 1 to the don't care. B is constant and CD is constant. I am moving from one position to the another position, then the value will be B, C, D. And when we are using the don't care, then the output will be A plus B, C, D. So simply looking into the Boolean expression, we can find out that here we are using only a 3 input AND gate and an OR gate. So here the hardware requirements are reduced when we are using don't care. Although as hardware requirements are reduced, the output will be same, but it will cost less. Complexity will be reduced and the hardware cost will be reduced. So whenever you are using don't care conditions, if there is a possibility that don't care conditions are getting paired with anyone, then you can pair it. If there is only don't care, then left it. Or don't care can be paired only and only with SOP or POS. There should be no pairing of don't care only. That should be kept in mind. Move to the next topic. As we have done the pairing or the K-map minimization with the help of SOP, the same can be done with the help of POS, product of sum minimization, and the manner is same. The approach are much the same as SOP, except that POS expressions, zeros representing the standard sum terms, are replaced on the K-map instead of 1. So SOP is represented by ones, and on the other hand, POS is represented by zeros in the K-map, and the same will be mapped into the K-map. Suppose we have an expression A plus B plus C. It is nothing but in case of POS, it will be 0, 0, 0. Now the next term is A plus B bar plus C. It will be 0, 1, 0. Next we have A bar plus B bar plus C, and A bar plus B plus C bar. So what we have to do, we have to just write their corresponding binary value. Then we have to map it into the K-map. The first value is 0, 0, 0. It is here 0, 0, 0. 0, 1, 0, 0, 1, 0. It is here 1, 1, 0, 1, 1, 0. It is here, and 1, 0, 1, 1, 0, 1. 1, 0, 1 is here. So the mapping is same as in case of SOP, but instead of ones, we have to write 0. Is that clear? Okay, let's move. Now, how to minimize and how to find out the simplified expression for the POS with the help of K-map, and the process will be same. We have to make pairs. So here, instead of ones, we have to make pairs of the zeros. Now suppose this is your expression. Sorry, a plus b plus c, that is 0 0 0 is here. A plus b plus c bar, so 0 0 1, so 0 0 1 is here. A plus b bar plus c, so a 0 1 0 is here. A plus b bar plus c bar, that is 1 0 0, so 1 0 sorry 0 1 1, so 0 1 1 is here, and we have a bar plus b bar plus c bar, that is 1 1 0, so 1 1 0. So these are the zeros. Now with this example I have just tried to explain that with the same k map we can find out TOS and SOP both. So whatever is left is the SOP. So there, if there are 5 ones in a 3 variable K map, sorry, 5 zeros, then there should be 3 ones. So with this single example, I have to try to solve both POS and SOP with the same K map. So when we solve for this pair, we have to find out which variable is unchanged. When I move from here to here, B is changing, that is A is unchanged 0. When I'm moving from this column to this column, C is changing. So I have left only with the A, and a value of A is 0, that means it is represented by A. Now for this pair, when I move from here to here, A is changing, B is constant, and C is constant. So B is 1, C is 0. So the value will be B bar plus C. Now the expression in case of POS form, it will be A B bar plus C. Similarly, when we have to solve in the form of SOP, then we have a pair. Again for this pair, AB is constant, then it is AB bar. For this value, A and C are constant, then the value of AC. So this is the way how we can make pairs of SOP and POS in the same K map, and it will always be given and asked with the question that in which form you have to solve your expression. So this topic NAND and NOR gate as universal gate you have studied in your first year electronic circuits, and it is for your home assignment. You will be provided notes, and you have to study it at your yourself. Then we'll discuss that how NAND and NOR are called as universal gate. So the next topic we are going to discuss is Quine-Mikulski minimization or tabulation method. And remember it that one question of 12.5 marks from unit 1 will be in the examination from this particular method. The marks will be 12.5. 12.5 number का question आएगा on Quine-Mikulski method. And the beauty of this particular method is that you can verify your answer by solving the same Boolean expression with the help of K-map. So what you solve with this particular method, you can compare it or verify with the help of K-map. So what happens when the number of inputs vary beyond 5 and 6 variables? So it is very much difficult to solve a K-map with 5 input variable or more than 5 input variable. So in that case, we develop an algorithm, and this is that's why it is called a tabulation method. And we do step by step as per the algorithm, and we can solve a Boolean function with the help of tabulation method. Now, Quine-Mikulski minimization. It is we have two-step process utilizing tabular listing for identifying prime implicants, that is called prime implicant table, and identify minimal prime implicant set. So we have to make two different tables. The first table is implicants table, and another one is prime implicant table. Now, all work is done in tabular form. Number of variables is not a limitation, means how many number of input variables are there, there is not a problem. Basis of many computer implementation is done with the help of tabular method, and don't care conditions can be easily handled with the tabulation method. Now proper organization and term identification are key factor for correct result. Now the process, the terms are initially listed one per line in groups. Each group contains terms with the same number of true and complemented variables. Terms are listed in numerical order with group. When we'll solve it with the help of the example, then it will be pretty much easier. Now terms and implicants are identified using one of three common notations. First notation is full variable form, another is cellular form, and the last one is 1, 0 and dash. So how dash comes into the player, that is the don't care condition. When we solve with the help of the example, then it will be pretty much easier to understand. So suppose, let us come to the example. Suppose we are given an example, f of a, b, c, d, that there are 4 input variables. So this is defined by summation, means sum of product 4, 5, 6, 8, 10, 13. So these are the input SOP. So 4 is nothing but 0, 1, 0, 0. That is 4. 8 is 1, 0, 0, 0. 6 is 0, 1, 1, 0. 5 is 0, 1, 0, 1. 10 is 1, 0, 1, 0. 13 is 1, 1, 0, 1. So the very first step is write full variable value, cellular value, that is its min term, and its 1, 0 values. So what we do, we make groups, and this is your first group in which we have only single one. So 4 and 8 have single one only. In the next group, we should have 2 ones. So in the value of 5, 6, 10, we have 2 ones. And in the third, we have 3 ones, that is 13. If there is a possibility, next group will be of 4 ones, and the next group will be of 5 ones. So we have to arrange in the increasing order of number of ones. These are the groups. We have to segregate all groups. That is a table. So in this way, we have to segregate. So here we have 3 groups. So very much first step will be, the first step will be write the binary value of the min terms, its equivalent full variable value, that is true and complemented value, and arrange them in increasing number of ones. If there was 0, so the first group will be 0, 0, 0, 0, like this. So let us take an example with a full example. Suppose we are given f equals to a, b, c, d equals to summation m, that is the min terms, 4, 5, 6, 8, 9, 10, 13. What was the last example? And summation d, that is the don't care, 0, 7, 15. So in the first implication table, we have to represent all numbers. So in the first part, find the prime implicant tables. So this is your 0, because 0 is don't care. That is the first group. Next is 4. 4 is 0, 1, 0, 1. Then 8, 1, 0, 0, 0. That is the second group. Next group is 0, 1, 0, 1, 5. 0, 1, 1, 0 is 6. 1, 0, 0, 1 is 9. 5, 6, 9. Then 1, 0, 1, 0 is 10. That is 10. So group 1, group 2, group 3. Group 4 will be of number of 3 ones. So 7 has 3 ones, 0, 1, 1, 0. And 13 has 3 ones, 1, 1, 0, 1. And we have 15, 1, 1, 1, 1. So this is the first step when we are making an implicant table, and note that the don't care conditions are included in this step. That should be kept in mind, that we have to include all don't care conditions, and we have to arrange them in increasing number of ones, and we have to make groups. So you can write it like either like this. In case of tabular method, cellular method, 0, 4, 8, 5, 6, 9, 10, 7, 13, 15. So this is your binary value. This is your cellular value. Or we can write it like in it's your 1, 0 value. So 0 is represented by 0, 0, 0, 0. 4 is 0, 1, 0, 0, 0, 1, 0, 0. then 8 is 1 0 0 0 like this. So we have to, we can represent it like this. These are the 1 0 values. Now we have to make the column 2 of this particular table. We have to compare first group with the second group, and we have to find out the number of single bit change. So where there is a single bit change, that position will be dash. So apply adjacency, compare element of group with n ones against those with n plus 1 ones. One bit difference implies adjacent. Eliminate variable and place in next column. So we have to compare 1 with 4. So when we compare 1 with 4, so in the second position it is 1. So value will be 0. This value is changing. So we have put a dash 0 dash 0 0, and we write in bracket 0 comma 4. So this is your comparison. Then we compare 0 with 8. The value will be dash 0 0 0. And it is, when we compare this with this is healed. Now this first group can never be compared with the third group, because we have a difference of 2 ones. So this group can be compared with only next adjacent group. Now what we do, we compare this group. Now what happens, whenever a comparison is find, put a tick mark, means these 3 groups has been compared with each other. Now compare 4 with 5. Is it possible? Yes. We have 0 1 0 and this bit is changed, then the value will be 0 1 0 dash 0 1 0 0 0 1 0 1. The value will be 0 1 0 dash. We'll find to compare 4 with 6. Yes, we can compare. The value will be 0 1. Third bit is changed, 0 1 dash 0. Can we compare 4 with 9? No, 3 bits are changing. 4 with 10? No, 3 bits are changing. Now we compare 8 with 5, 3 bits changing. 8 with 6, 3 bits changing. 8 with 9, yes, single bit change, and the value will be 1 0 0 dash, because LSB is changing 0 to 1. So this is 1 0 0 dash. Then again 8 with 10, yes, 1 0 dash 0. Similarly, you can see that all these group 3 elements are compared with group 2 elements. So we have ticked all the elements. Now compare group 3 with group 4 and again look for a single bit change. So 5 is 7. Yes, we can change. We can match. Value will be 0 1 dash 1, 0 1 dash 1. 5 with 13. Yes, we can have dash 1 0 1. So we have ticked both. We have ticked 5, 7. Tick is 13 now. Tick. Now we move to the 6 and 7. Yes, we can 6 and 7 can be changed. Yes, 6 and 7. 0 1 1 dash 0 1 1 1 to 0 1 1 dash. We have ticked on this. Now 6 by 13. Yes, it can, no, it cannot be changed. Then 9 by 7, no. 9 by 13, yes. So it can be 1 dash 0 1. So whichever values are compared, we have to put tick. Again, group 4 is compared with group 5. Both can be 7 with 15 dash 1 1 1. 13 with 15 1 1 dash 1. So these value can be put it like this. So we have this much of combination. 0 is compared by 4, 0 is compared by 8, 5, 4, 5, 4, 6, 8, 9, 8, 10, 5, 7, 5, 13, 6, 7, 9, 13, 7, 15, 13, 15. So all column 1 is eliminated. Now we have nothing to do with the column 1. Again, the same process is done. That means we have to compare group 1 in the next column to the group 2. And the condition is that the position of dash should be same and we should look for a single bit change. Now suppose 0 versus 4 is okay. Then it will be much easier when we are going to doing with the example. So again we write now the position of dash should be same and we should look for a single bit change. Now 4, this value cannot be matched with any of the group 2 because dash position should be on the second position, which is not true. Again, this value cannot be compared with the group 2 dash 000 because nobody in dash in the group 2 has dash on the MSB. Now we have to compare this value with the next group, and this value can be compared 0 1 0 dash. So dash should be on the last one, 0 1 1 dash. So this value can be compared. So 0 1 0 dash can be compared with 0 1 1 dash, and the value will be 0 1 dash dash because both these bits will be changing variable, then the value will be dash dash 0 1 dash dash. So we have put tick here and we have put tick here, and we consider we do considering the same exercise, and now the condition comes like this. So we have compared 4 5 with 6 7, then 4 5 is compared by 6 7. Similarly 4 6 will be compared by 5 7. So we have to write this value only single time. We need not to repeat the value because the value will be same. Then 5 7 will be compared with 13 15. So 5 7 13 15 and 5 13 7 15. The value of the output will be same. So you can see here the value of the output is same, dash 1 dash 1 0 1 dash dash. Now we try to there are two different columns. We'll compare in column 3 group 1 with the group 2, but again we can see that the position of dash is not same, so no next comparison can be done. So we mark in the next step what are the unmatched values. So we have 1 2 3 4 5 6 7. So these are the 7 combinations which haven't been matched or which are not comparable. So now next we have to make a implicant table like this. Okay, fine. So when we you solve this with the help of the K-map. So the K-map will be look like this. We have put it don't care with cross and SOP with the help of ones. So need not to bother about this. Now what we have to do, we have to make a prime implicant table, that is the coverage table. So we write all the main terms given in the SOP. These are the SOP, and don't include don't care condition in coverage table. So we have to look only for the input combinations, that is SOPs 4 5 6 8 9 10 13. So we can look from the example what was the our example exact example, the 4 5 6 8 9 10 13, and the rest of the don't care condition 0 7 15 are not included in the coverage table. So write it on the top of the table, write whichever combination is not yet compared or which is unmatched. So we have we can look here. So we have 0 4 0 8 8 9 8 10 9 13 4 5 6 7 5 7 13 15. So these all values will be written in the table. 0 4 whose value is 0 dash 0 0, 0 8 value is dash 0 0 0, 8 9 value is 1 0 0 dash, 8 10 1 0 dash 0, 9 13 dash 1 dash 0 1, 4 5 6 7 0 1 dash dash, 5 7 13 15 dash 1 dash 1. And write across where there is a value, because 0 was the don't care, we don't care about this. 4 we put across. In the next 0 8 we put across between 8 8 and 9 8 and 9, then 8 and 10 8 and 10, sorry 8 and 10, 9 13 9 and 13, 4 5 6 7, then the 4 5 6 7 is don't care, 5 7 13 15, 5 7 is don't care, 13 and 15 is don't care. So we have to put cross below underneath the whatever term is in the don't which haven't been compared yet. Now this is what we have done. Now with the same table, you just mark a cross which has in a single column which has a single cross. So here we see in the under the 4 we have 2 cross, we leave it. Under 5 we have to cross, leave it. Under 6 we have only cross, we have to cross it, and we have to circle the SOP term. Then under 8 is 3, under 9 is 2, under 10 it is 1, so we have corresponding term 8, 10. Under 13 it is again 2. So we get only 2 terms which has been circled. If the column has a single X, then the implicant associated with the row is essential and it must appear in the minimum coverage. So these are the agential prime implicant. When you'll get a question that find out the agential prime implicant and the prime implicant, then you have to do this process. So these are the agential prime implicant which should be included in the final answer. And next we'll find out that whichever pair has been left. So we see that when we look into this, so we have to find out that whichever is covered. So 8, 10. So 8 is covered, we have crossed it. 10 is covered, we have crossed it. 4, 5, 6, 7. Then 4, 5, 6, 7. We don't care. So we are left with the 2 min terms 9 and 13, which are not covered in our final answer. So what we do, we have to look into the any variable which has both terms common. So suppose in this case we have a 9 and 13. So 9 and 13 are 2 missing min terms. So we can find out that if we include 9 and 13 in our final answer, then it will be pretty much easy that we cover all the min terms. So what we do, we choose 9 and 13. So 9 is covered, 13 is covered. So this is your final answer. And corresponding 8, 10, we have A, B bar, D bar, A, B bar, D bar. For the 9, 13, we have A, C bar, D, A, C bar, D. And for 5, 4, 5, 6, 7, we have A bar, B. So this is your final answer. And when you solve it with the help of the K map, you can find out, or you can cross verify what should be the final answer B. So you can solve this example with your own, and you can ask me if you are facing any difficulty. This is a practice example that you have to do with yourself. Now simplify the Boolean expression using Quinn-McCluskey method, that is the tabulation method, and we are given f equals to a, b, c, d summation min terms 0, 1, 3, 7, 8, 9, 11, 15. And the answer should be y equals to, or f equals to b bar c bar plus cd. You note down this question and note down the answer and match your answer, and further verify your answer with the help of the K-map. So I think we should stop our lecture here.